Yeah, looks great. So we've got Kaylin Jones, who will tell us about the project that she worked on this summer with Yi Hong and Eric Anderson. Welcome, Kaylin.
All right, so hi everyone. My name is Kaylin Jones. I am entering into my second year of a PhD at the University of Michigan in the Environmental Engineering Department. And this summer, I worked with Dr. Eric Anderson and Dr. Yi Hong on a project entitled Toward Flood Resilience in Great Lakes Coastal Regions, Numerical Modeling of Flood Risks in Different Zones Under Climate Change. So recently, the Great Lakes region has experienced an increase in flooding, and that's mainly due to an increase in water levels on the lakes. So this couple of graphs to the right from the Army Corps of Engineers, which you can see all the lakes, the red line here represents the long-term average lake level. And the blue squiggly lines represent the monthly mean every single month for the last 100 years of the lake level. Now in the last 6 years, which is the part that's boxed in red, you can see that on every single lake, the mean has been above the long-term average and it's been trending upward. So for my project, we focus on Lake Ontario. So here at the bottom, I have a bit more zoomed in view of that lake. So the purple dot on these graphs is the long-term average. The blue line is the 2019 levels. The red line is the 2020 levels. And the two black horizontal lines are the high and low reported. So as you can see, this year, Lake Ontario is not experiencing very high levels or extremely high levels, but last year they really did. So if you notice that the June black line representing the high and the blue line representing the 2019 level, they coincide. And that's because last year set a record for the highest level ever recorded in June. And this picture to the right shows that this flooding really is having real impacts on people. So here's a community nearby Lake Ontario in that month where you can see that the entire road is completely flooded. However, to predict this flooding, there is currently only two tools. So there's currently one called the Lake Level Viewer and the Lake Flood Mapper. And I'll get into what these are in a second. And that's what planners currently have in order to give these communities warning for what they should do. However, this summer we worked on developing two more. So the first one used the current operational lake level models, and the second one we worked on expanded these models. And once again, I'll get into what those are in a second. So the first tool that we have, the Lake Level Viewer, is a NOAA tool that's based solely on water level. So the way this tool works is it basically takes the lake and it fills it up just like a bathtub to whatever level you say to fill it up to. And so it has the entire lake at the same level, it's static, and it says, okay, under these conditions, where will it flood? So as you can imagine, lake water level is an important aspect in flooding. However, this is a pretty unrealistic way to look at lake water level because lakes are not static. It's not the same level for the entire lake, and those levels are consistently changing. So this tool essentially takes one small piece of the puzzle, an important piece, but a small basic piece, and misses out on a lot of the complicated physics that really do go into flooding. So next we have the Lake Flood Mapper. So in the way that the Lake Level Viewer only took into account water level, the Lake Flood Mapper only takes into account wind. And the way this tool works is you put in that the wind was either between 0 and 10 miles an hour, or 10 to 20, and you say it was mainly going east or it was mainly going northwest. And this tool will then say, okay, under these conditions, where will this flood? But again, that's a really small piece of the puzzle. And also wind doesn't work that way in reality. So while it is a good basic, it misses out on a lot of the aspects that really are important to flooding. So we wanted to try to get into those more specific details to get a more accurate prediction on what flooding will occur. So like I said, the two that we developed this summer use the current operational model. So what is this model? Well, it's called the Finite Volume Community Ocean Model, or FVCOM, as I'll refer to it from here on out. And FVCOM is a model that uses an unstructured triangular grid. So here's an example of the grid to the right. What unstructured means is that the triangles can be all different sizes. So near complicated shorelines, we are able to have smaller triangles to more effectively resolve this complicated geometry. Whereas in the center of the lake, where you don't need such a small refined grid, you can have larger triangles. And this allows us to reduce computational expense and let the model run quicker than it would have otherwise. And these models work great. They're really good. So you can see the graph to the bottom is comparing for the month of June last year, real data versus the model's output. So the blue line is real data and the orange line is what the model said would happen. And while they're not 100% on at all times, they track really well. And it's typically plus or minus an inch. And when you're looking at the scale of the Great Lakes, plus or minus an inch, that's really good. That's a great model. However, the current models only include the lake. The grid goes up to the shoreline and it stops. It effectively sees a wall. So it's not able to predict flooding on the land on its own. So in order to predict that flooding, we need to combine it with land height data. So that's a tool that I personally wrote this summer. So here's my really complicated mathematical formula to explain it. So as you can see, we take the FVCOM grid, we combine it with land height data, and what my tool spits out is what you see to the right. It gives you an area that is flooded on land. It spits out a KML file, which is just a type of file that you can open in Google Maps that will show the area you can expect to be flooded. The way that my tool does this comparison is along the shoreline you're interested in, at every FVCOM node, at whatever time you want, you take the water height level that a VCOM tells you, you compare it to nearby land height, and you say, okay, if the land is lower than the water height, it's going to flood. And if it's higher, then it's not going to flood. And so we developed this tool for 3 vulnerable shorelines. The way that we pick these shorelines is looking at the 2 previous tools. These areas are pretty susceptible to flooding, even under relatively mild conditions. So we decided that these would be good for comparing. So this is the tool with the current grid. In order to predict flooding on this grid, you need additional land height data. But we don't want that. We just want the grid to be able to predict flooding on its own. So we expanded the grid out to include some land area. So here's the original grid, and here is the expanded grid. So you can see that we expanded out into land. It got expanded out to the 20-meter contour, and that's because it's really unlikely that you'll see flooding past this. So this does encompass all of the land that would be necessary to get the full flooding picture. And now this model can directly predict flooding. In the output, it will say whether every node in the model is wet, which means it's flooded, or it's dry. And so like I said, we looked at 3 different shorelines. So here are these 3 shorelines. The first one I called the Eastern Shoreline. The second I called the Rochester. And the third I called the NOTL-Olcott. So the reason I called it that is that on the left side is Niagara on the Lake, so NOTL, Niagara on the Lake. And on the right side is Olcott, New York. So while I developed that tool using the original FVCOM grid for all 3 of these shorelines, the expanded grid near the Rochester shoreline, we got really weird, invalid results. It was basically telling us that the middle of the lake should be dry. So in order to have any kind of meaningful comparison on these 2 tools, we only looked at shorelines 1 and 3. So first, looking at shoreline 1, we looked at the shoreline under the real conditions experienced on June 1st of last year. So the image to the left is the result from the lake level viewer. The image in the middle is the result from the lake flood mapper. And the image on the right is the result from both FVCOM tools. The white outline shape is the tool using the original grid that I wrote, and the red shape is the tool with the expanded grid, what the expanded grid said would happen. So I really only used the lake level viewer and the lake flood mapper as a means of seeing if the code that I wrote using the original grid was giving a realistic output. And if you look at the shape that the flood mapper gives and the white shape on the right image, you can see that they're really similar. So looking at this, I basically decided, okay, the code using the original grid does give a realistic view. It can be used as a good metric to determining how the expanded grid is performing. So from there on out, I really only compared the expanded grid to the code using the original grid. And as you can see, the expanded grid gave less flooding than the original grid. So the original grid said that there would be about 10.8 square miles of flooding, where the extended grid gave about a third of that. It gave 3.4 square miles. And the original grid said that you could expect flooding up to 2.3 miles inland, whereas the expanded grid said that you can only expect it about 1.5 miles inland. And this is a good result. This is what we expected to see. And that's because the original grid, it doesn't take into account any friction over land. It doesn't take into account the fact that as flooding goes inland, you're going to lose water level, you're going to lose momentum. But the expanded grid is able to take that into account. So the less in flooding with the expanded grid is what was expected. So this was good news. This is what we want to see. So like I said, for this shoreline, we looked at real conditions. However, for the NOTL-Olcott shoreline, we could not do that. That's because real conditions on the shoreline did not produce any significant flooding, so we could not use them as a way to compare the different tools. So what we did is we ran all the tools with a false wind. We ran a 25 meter per second wind coming from the north, going south, so it would directly hit that shoreline for a week. So we effectively forced flooding on the shoreline. And even though these are fake conditions, that's still okay because we ran every tool with the same conditions. So because we're really using this as a way to compare different tools, because they were all ran the same, it's okay that the conditions aren't real. And so again, I really only use the flood mapper and the lake level viewer as a way of seeing if my code was giving a realistic output. And as you can see, they both basically show mainly the beach is flooded and a little bit further inland is flooded. So I once again decided, okay, I'm just going to use my code as the metric for seeing how the expanded grid is performing. Now, as you can see to the right, again, the red is the expanded grid and the white is the tool using the original grid. The expanded grid gave these two discrete areas of flooding. So I'm going to look at these two areas separately. So the image on the right is the area that was to the left of that shoreline. And this pretty much tells the same story as the eastern shoreline. You see reduced flooding, we believe, for the same reasons that you saw along the eastern shoreline. However, the picture on the right tells a different story. We see something a little different. You'll notice that the expanded grid shows flooding in some areas that is more inland than the original grid. And while this at first seems counterintuitive to the explanation that we just gave, this is also reasonable. It also makes sense. And that's because of the way that the wind forcing works in these two models. So the original grid only sees wind over the lake. It basically says that, okay, the only wind that can pull on this water and pull it inland is acting up to a certain point, and then it stops, and then the water freely floods in. However, in reality, wind acts over land too, and the expanded grid is able to see that. So it says, okay, yeah, this wind is pulling on the water while it's on the lake, but it continues to pull it when it's inland. So it's able to essentially pull it farther in. So that's why we see some more inland flooding with the expanded grid in this area. However, overall, you still get the same idea of the expanded grid giving less flooding. So now that we see that the grid is acting semi how we expect it to, what are the next steps with this project? I sadly will not be involved with. So the first step is we need to troubleshoot the issues. So like I said, by the Rochester shoreline, we are getting some really weird results. So looking at that, finding out what's causing these issues, and just making the grid more robust across the entire lake. Because if we want to have this model accurate, you need to have it working on an accurate grid. Next, we need to improve the way that friction is modeled over land. Right now, the way FVCOM models friction is it's depth-based. It's based on the water depth. And this is a great model if you're in the ocean and you have a sandy bed. But when you get to land where there's trees and houses and roads, it doesn't work as great. It's not as accurate. So calibrating this friction within the model will then better be able to resolve where the water is able to reach. Next, none of these tools involve wave current interactions. And as you can imagine, waves are important to flooding, right? A wave comes inland, brings a lot of water with it all at once. So the model being able to see these interactions to include this will again make it more accurate. And finally, we need to expand these tools to the other Great Lakes. Right now we're focusing on Lake Ontario, but the other lakes flood as well. So putting this onto the other lakes is the next step. All right, so I want to thank my mentors this summer, Eric and Yi. They were really supportive. They were really patient with me. They gave me any files I needed, answered any questions, and I really appreciated being able to work with them as they were really kind and smart. Next, I want to thank my advisor at University of Michigan, Dr. Aline Kotel. I would not have known about or applied for this fellowship if it wasn't for her encouragement, and she's just been very supportive this summer. And finally, I want to thank Mary and everyone at GLERL and CIGLR that made this fellowship happen, that made it happen successfully, and that helped me, and I'm sure the other fellows, still feel welcomed and like a part of a community despite being online. And that's what I have for you guys. Thank you.
Thanks so much, Kaylin. That is the last and final time I'll make that mistake. We have two Kaylins and a Caitlin, so I've been struggling with it all summer. So everyone's been very patient and letting me laugh at myself with it. But Kaylin, fantastic job, and thank you so much for telling us about your project. Super interesting and great job. So we've got time for questions. If anybody has questions for Kaylin, please raise your hand or type them in the chat box. We'll leave a few moments for you to collect your thoughts on that. We have Devin Gill says, great presentation, Kaylin. I like your communication style. Thanks for that comment, Devin. And Ayumi Minomi says, great talk. Thank you, Ayumi. And Ayumi does have a question too. Ayumi asks, did you try alternate wind direction for the 25 meter per second northerly wind?
Yeah, so we did try quite a few different runs, and that was mainly because we were trying to get that Rochester shoreline to flood normally. So we tried some winds coming in from the northeast at 30 miles an hour, 30 meters per second. We also actually tried a 55 meter per second wind because that speed has been seen on the lakes like under hurricane conditions, like under Sandy, and that basically crashed the model because it was way too fast. So we did try some different conditions. We still saw similar results on the NOTL-Olcott shoreline, even though that was not the aim with those conditions.
Great, thank you. Let's see. Debbie Lee says, great talk, very timely given the high lake levels. And she asks, are there further plans for sharing this tool or making it available?
I'm not sure. I would hope so. I think once it's more developed, it would become a more widespread tool. Yeah.
Right. Thanks, Kaylin. I'll just give it a few moments here to see if we have any other questions come in. Okay, I don't see anything else coming in. So again, if there's something, if we move on too quickly here, feel free to type them in and we can follow back up with Kaylin later. Thanks so much, Kaylin. You can end your